My name is Bhaskar Vairamohan. I am with the Electric Power Research Institute located here in Knoxville, Tennessee, USA. Um, just to make sure, am I audible and clear to everyone? If you can just say yes, that'll be great. Thank you. Thank you. So today, in the next 40 to 45 minutes, what I would like to cover is to talk about ultraviolet and electron beam curing of coatings, which, as Hans mentioned, is a very specialized area, and see what are some of the new trends that are developing, what are some of the basics about ultraviolet curing, what is the market potential, where is the growth opportunities, and some of the roundup from one of the conferences held in USA called RadTech 2014. That conference roundup will be also presented. Some key highlights will be shared with you folks. So let's um, move here to the next slide here. So I want to take a minute or two to just talk about who EPRI is and how and which part of EPRI that I belong. EPRI was started in 1972 as an independent organization, which is also non-profit for serving public interest, energy, and environmental research. And we work with a lot of electric utilities, both nationwide and internationally. Our mission is to advance safe, reliable, affordable, and environmentally responsible electricity for society through the collaboration, thought leadership, science, and technology innovation. We have members spanning across 30 countries, nearly 450 plus utility members, and we have a significant international membership as well. Nearly 25% of EPRI's research and development funding comes through international members. There are three key aspects of EPRI if you think about it. One is independent, which is unbiased, objective, scientific testing of different technologies, addressing reliability, efficiency, health, safety, and environmental aspects of the electric generation, distribution, transmission, and end use. The second one is non-profit. We are chartered to serve the public benefit. And the third one, which is also very exciting, is the collaborative effort, bringing together scientists, engineers, academic researchers, and industrial experts together. And this engagement that we are having today and the ability to, for me, to come and share some of our work in this area can be considered as a collaborative effort where our knowledge is shared with you and you can provide feedback on that. So that kind of collaboration is welcomed in many of our members. So let's go into the basics of ultraviolet and electron beam curing. And this is a very specialized area where before going to the basics, where do you see the ultraviolet and electron beam curing? If you say yes to any of the three things, then you have touched and felt the ultraviolet curing. If you have used a DVD or a CD disc, if you have a phone, if you use automobile or car, if you used any of this, and if you say yes to any of this, then you have used the product, the byproduct of UV curing. All the cell phones and CDs and DVDs and numerous other applications are there for ultraviolet and electron beam curing. So we'll take a little bit peek about what is it and how is it applied. Not going too deep into the chemical structure, which could take several hours for me to explain, but rather we will talk on the high level technology overview, just enough to know what it is, and then talk about some of the niche market applications that we are seeing. So UV is available everywhere, and the natural source of that is our sunlight. Scientists divide the UV spectrum into three different distinct regions. They call it UVA, UVB, and UVC. There's three different regions. And this UV spectrum falls beyond of our visible light spectrum. So it is not visible to our human eyesight, but some insects like bumblebees are shown to see this kind of UV light. So what you see below, the picture shows the different part of the UV spectrum. And the UV spectrum ranges from 100 nanometers to 400 nanometers. So 100 nanometers to 280 nanometers is the short wave or the UVC spectrum, and 280 to 315 nanometers is considered the medium or UVB spectrum, and 315 to 400 nanometers is UVA or the long wave spectrum. In UV curing, the ultraviolet energy in terms of photons or to near visible light is used to form a coating, a film, or cure and dry an ink product. This UV replaces thermal oxidative evaporative curing that is traditionally been done in the industry. Alternative to UV is also electron beam, which has some high energy electrons and used to initiate the curing process. So to give you a more detailed explanation of how this happens, this curing process, the UV radiation is emitted by and absorbed by valence electrons of atoms in the formula of the coating. When an electron in an outer atomic orbit encounters a photon from the UV light source with the right amount of energy, the electron will absorb that photon and move from its normal state to an excited state. If the photon has enough energy, then the electron will leave the atom of the formula of the curing component or the chemical compound and entirely become a free electron or a free radical. And this free radical is what is helping in the polymerization process of bringing all the components together and making a polymer. And we will talk more about it in the next slide with some pictures that show you how this free radical is helping in the polymerization process. The typical sources for the UV light most commonly is the medium vapor mercury lamp. And this medium pressure mercury vapor lamp is the traditional lamp, but it is currently seeing a different trend. The light emitting diode, the UV based light emitting diode, is a very lucrative option where it has a low power and provides the same kind of spectrum for the UV range. Not only that, it has different control schemes that could help in having specific location to be cured. So the LED gives different options to the industrial facilities. And also there is an electrode arc or microwave energy could also be used to cause the UV emission. So these are some of the common sources for UV. So now that we know about UV, what is curing and how these two come together? Curing is a set of chemical and physical process that the coating materials must undergo after drying. And the coating must attach itself to the substrate physically or chemically and must cohere to itself as well. It also needs to undergo a chemical reaction called polymerization. These processes are collectively known as curing. Depending on the chemistry of this material, curing can take place either at room temperature or at elevated temperatures or by free radical reactions such as ultraviolet or EB. So curing by EV or electron beam or ultraviolet is just one of the ways. Traditionally, the way curing happens, if you have a painting on a car, automobile, and if you want to cure it, it has a two-step process. In the first step, the solvent-based paint is dried first to remove any moisture or any solvent. And the second step, it is gone under the part to be cured goes inside the oven and thermally cured so that the coating adheres to the surface. Most of the industrial coatings are thermally cured. With thermally curable coatings, adding the heat can accelerate the curing process, but care has to be taken because sometimes overheating could cause defects on the coating. So going from thermal to a non-thermal process saves lot of energy. It's a very energy efficient process. What are the basic requirements for UV or EB curing? There are three important elements in coming to a requirement phase of the UV or EB curing. First, the application. The application, when I say application, is it a cell phone case that you want to coat with a UV curable coating, or a CD or a fiber optic cable? So each of them have a different requirements, and so the application itself determines what kind of energy level, what kinds of formulation that goes into it. The second area is the energy source. So would you like to go with ultraviolet based curing or electron beam curing? Even though I say this together, ultraviolet and electron beam, they both have some distinct differences between them. They are not one and the same. The ultraviolet use the ultraviolet light emitting light emitters, whereas electron beam provides low energy or high energy electrons. So there are two distinct different technologies. But in this case, we are going to treat them as one because they use similar formulations. So when I talk about formulation, it is the chemical compound or chemical components that makes up the coating material. So the formulation has several elements which we will see in a minute. So these three elements have to work together, and the specifications of each one of them determines what kind of the coating material, what kind of energy source is required for that individual application. And formulating a UV curable coating powder or a compound is also a very involved process. It is not just made of one chemical compound, but rather it is made of four distinct different major components. It could be more than four, but these are the main four that goes into the UV formulation. The first product is called the oligomer. The oligomer is just a polymer or a polymer intermediate containing few structural units. And I will show in the next few slides about how they look. A polymer is, and the monomer is a molecule that may bind chemically to other molecules to form a polymer. So in order for a monomer to combine together to form a polymer, there needs to be some reaction and addition. So additives are chemical agents such as color pigments, fillers, wetting agents that add various properties to the coating, and they call this the performance tuning. The additives are very important to impart various properties to the coating. For example, if you are taking a cell phone case, one of the important specification is it needs to be scratch resistant. So that kind of scratch resistant properties or color. Nowadays the cell phones come with different colors. So adding different pigments to make it a different color product, all is done through the additives. And finally, a most critical part of the UV curable system or the paint or the compound is the photoinitiator. This is a chemical compound that decomposes upon seeing the ultraviolet light into free radicals. So these free radicals are the reason why how the monomers can link together with the adhesives and oligomer to form polymerized structure. So you can see the picture on the right, which shows different molecules and different sizes. Initially, they are not, before the application of the UV light, each of these molecules are not touching each other, and they are individual components. So they are powdered materials. They are not touching each other. They are not connected to each other. And you can see wherever it says photo, that is the photo initiator. So the role of photo initiators is very, very key and important in this UV process. The photo initiators absorb the UV light to form the free radical, and they initiate the free radicals initiate the polymerization process by attaching themselves or adding themselves to the monomers and oligomers. It has to be noted that different photoinitiators absorb UV at different wavelength. So the peak wavelength is determined by the application and what kind of energy that is needed. And an interesting thing is they have long shelf life, so they can be stored for a long time, and they have the long shelf life because they only react with UV light, the wavelength. So if you keep it outside, it may not get damaged. So they have a long shelf life. So this slide shows how different components merge together with the help of photoinitiator to make polymer. So the right top picture shows the UV adhesive material that has photoinitiators um, um, and oligomers. So when the UV light is applied, what happens is there is the small photoinitiators start to create free radical and starts linking the big oligomers and adhesive structures. And when it is fully cured, you see a cross-linked polymer that is very that provides the required specifications of that particular adhesive. So another key important point of the curing process is that thermal processing is not necessary to cross-link the resins. Just the exposure to the photoinitiator and exposure of the photoinitiator to the ultraviolet light is just needed to start and complete the reaction. There may be some heat needed to make sure that the coatings are completely melt and flow and make sure it's a uniform spread, but it's not the same amount of thermal energy needed by the traditional thermal curing. So it is a very green technology and low energy usage technology. Let's take a few minutes to talk about electron beam curing and how it is different from the ultraviolet curing. In electron beam curing, you can see that the formulation is almost identical to the ultraviolet. It still has the oligomers, still has the monomers, still has the additives. But one thing that you may see that is not there is the photoinitiator. It's because the electron beams uses electrons, and the electrons are the free radicals actually. The electrons are the free radicals that can initiate this cross-linking process to make polymers. So the electrons can open up the double bonds and initiate the polymerization, and no photoinitiator is required. One interesting thing is that the electron beam systems can use the UV formulations to get the required properties. Even if there is a photoinitiator there, the electron beam systems can still work with the UV formulation. However, the UV system cannot work with the electron beam formulation because there is absence of photoinitiators. So sometimes the electron beam systems formulations are less expensive than the ultraviolet based systems because of the absence of photoinitiators, but the electron beam systems capital cost could be higher. But overall, for a specific application, they come to be very cost competitive and in fact advantageous over other thermal technologies. So here is a machine that could provide the electron beam. Um, the electron beam have ionizing radiation. They are low energy electrons. The sufficient energy to break the bonding and coating to generate the free radicals. It can penetrate into through a coating or ink through substrate, and it generates little to no heat, which is a very desired property, and it is controlled very precisely. So that's another advantage of electron beam, not affected by pigmentations or transparency of coatings or substrate. So because of the electrons involved, there are some of the advantages. So when all the coating is completed, the industry has a different mechanism to test how the curing has been completed and how successful it is, and what are the metrics to determine if the coating has been successful or not. So there are three distinct tests that I'm pointed here, but there are few other tests that I may not have listed. These are some of the most commonly used testing that I've come across. And the main one is the pencil hardness test. The pencil hardness test is exactly what you have imagined. A sharp pencil trying to go through the substrate, go through the coating and make scratch. And they have very different formulas to calculate how deep the penetration is and what kind of scratch it could cause. They also have something called the steel wool test, where the material that we use in the kitchen for steel wool could be used to create a scratch on the surface that was coated and see how much damage or how much scratch this has caused. And these are different tests just to make sure they increase the properties so it's scratch resistant based on different applications. So with that, the first section of the operations part was completed. Next, let's take a look at some of the existing applications and some of the emerging applications where the UV is becoming a very specialized area. One of the new areas that is getting a lot of attention these days is the 3D printing. The 3D printing is also known as additive manufacturing, where it's how it is different from the traditional manufacturing is in traditional manufacturing, to make a product, you take a block of metal or a block of wood and remove parts that are not needed to create the part using CNC machines or lathe or some kind of a milling tool to remove parts. This is in essence subtractive manufacturing. Whereas in additive manufacturing, the part is made or built one layer at a time, layer by layer. First, a 3D CAD file, a computer drawing has been made through the computer, and through a software, this file has been transferred to a printer that can understand this file and then start printing it. And like our traditional printers that print ink on paper, these are very specialized printers where the printer there's a build platform which I'll show in the next slide how it is printed. The outcome of that is um, the results are printed and you see the final product, and it may go through some post-processing to make sure uh, the specifications of that particular device or product that is made is within the specs. So here is how a 3D printer, especially for the ultraviolet curing, looks like. There is a build tray the build tray moves from top to down, and the movement is just one layer deep, and the layer is defined as the minim the layer, the thickness of the ink that is used to make that part. So a part is divided into many thousands of layers, and each layer, which is a small micron level thick, is built with that ink. And this ink, if you can see on the top, the head as a UV light. When this ink goes through and starts putting the part in the building tray, the UV cure, which can cure, cure the paint or the coating in just a fraction of a second, can form the layer one at a time. And every time the head moves back and forth and deposits the material, the UV light cures them. So you can see the part slowly starting to build, and when it is finally done, the build tray is down below and the part is on the build tray. And one of the advantages of UV based 3D printing, there are different ways of making 3D printing, but one of the advantages of the UV based 3D printing is, like our color printer, you can add different colors and print the parts with the multicolor. So that is one of the advantage of ultraviolet based 3D printing. There are a lot of new and emerging applications are coming up, specifically for ultraviolet and electron beam curing. One of the important thing that we have seen is a bio-inspired glue, and it sounds to be in a medical field, and it is you can check it out and doing Google search. This glue is a specialty patch, and this for fixing up large amount of bleeding in during surgeries. For example, if somebody is doing a heart surgery and if you want to close that leak, um, there are bio-inspired glue that gets activated within a few seconds of the ultraviolet light and can prevent uh, blood coming out of the heart. So there are different innovative emerging applications that are coming up. Similarly, for aircraft coatings, there is a shark skin coatings that could prevent uh, uh, what which can impart water repellent properties, snow and other repellent, and similarly there are so many more emerging applications coming up in railroad and other photovoltaic application, which seems to be on the rise. Some of the common existing applications are coatings for wood furnitures, coatings for plastic, metal, paper. So if you see this picture on the right, from the candy bar that you're eating, the wrapper has some kind of a coating, and it is cured with the UV or EB. The Lace chips packet to the pharmaceutical packaging, CDs, um, interiors of your automobiles, and so many different other advantages are there for UV applications. And some of the newer areas coming up in UV is roll-to-roll coating. And what do I mean by roll-to-roll coating is having a flexible or flexible coatings. For example, in the picture down below, you can see some of the uh, PV and solar cells uh, having a curing with ultraviolet, and lighting industry, medical industry, and even the display and touch screens of many of your tablets are getting a lot of coatings from ultraviolet. Let's spend a few minutes on what are some of the advantages of UV or EB curing, and what are some of the reason why it is still as um, um, remains as a very specialized industry. Uh, some of the advantages are much faster than thermal process. The curings, the coatings can be cured in a matter of seconds rather than minutes, especially for the bioglue kind of application that we are seeing in future. This is very, very critical because you want to seal a big puncture or big loss of blood, and it can done within fraction of second. That's much more important. Faster startup and shutdowns and lower energy consumption. Because thermal energy is not much used for curing, the UV lamps can be very low energy consuming devices, and also they can be instantly turned on and turned off, just like your lamp that you're using in your home. So virtually no energy or time lost waiting for it to come on and stabilize and things like that. Improved productivity. Because UV coatings cure in a matter of seconds, higher line speeds are possible. In fact, when I look at the electron beam processing, the coatings, the line speeds could be upward or uh, higher than 1000 feet per minute. So you can have very significant increase in line speeds. Less contamination and lower reject rates. There are no air movements or exhaust um, or any combustion is there, so there is less contamination and lower reject rates. This is in compared to the thermally cured products. Reduces or eliminates volatile organic compounds and solid waste disposal. This is a major problem in many of the industrial segment because uh, different environmental codes and regulations prevent the volatile organic compounds coming out of a paint booth or a painting application, because the solvent-based paint uses a lot of volatile organic compounds, and when they dry and they go up, they have to be burned so that it doesn't go to the atmosphere, which could cause pollution hazards and environmental safety hazards. So there are places called non-attainment areas, and for places like that, the non-attainment areas, UV technology could be a great fit because they are they do not contain solvents most times, and VOC emissions are very, very minimal, if not none, for them. So this is a very good green technology that could be used in the field. Uh, Less space required due to the speed of the cure. The systems require less floor space. Sometimes in the picture next following the slides, I have some pictures that shows how compact they could be. They offer superior finishes and also less thermal noise and air pollution. Finally, they could be used on temperature sensitive substrates. Uh, Materials such as wood and plastic are very sensitive to temperature. So directly you cannot have a coating and put it in a natural gas based oven, because they're very sensitive and there could be deformation or that could happen for wood or plastic. So for that kind of a temperature sensitive substrates, this is a great fit. UV and EB curing find a great fit. And even for fully assembled products that may contain gaskets and or fluids can be safely coated with the UV curable coatings. And in fact, an interesting example is um, nowadays the wine bottles um, with filled with wine have some of the new wine bottles do not have a paper label, but rather the paint is directly on the wine bottle, and it is the paint is sprayed on the wine bottle, and it is cured as it's going to the packaging. So it's because of UV curing. There is no thermal process that could degrade the quality of the wine, and at the same time you are increasing the line speed and you are eliminating the packaging waste. So there are so many distinct advantages of using the UV curing. So what are some of the reasons why it is not widely adopted? This is still a specialized industry. Um, the capital cost is still high for retrofitting, and this can be sometimes difficult for an application where maybe for a greenfield application it may work well, but for an existing brownfield application where you're trying to replace the existing natural gas or other thermal based curing into a ultraviolet curing, the chemistry and everything is changing, so it maybe bring some additional cost, which sometimes um, without some incentives the industry may not go for it, the industrial customers may not go for it. um, However, even though the system's capital cost is expensive, they have a very good competitive advantage over other applications, but still the first cost is an hindrance to the adoption. Second is the inks and coatings could be also expensive per pound because of the use of photo initiators and other different components. Retraining of operators is another area that is causing some concerns because the UV and EB inks or coatings perform differently compared to conventional inks and coatings. So these are some of the reasons why it is not widely adopted. However, in areas where it is used, they have shown extremely beneficial results and superior results compared to other traditional ways. So in the next few minutes, let's look at how this industry is looking for in terms of growth and what is the current status of the industry. If you look at a growth trajectory comparing the last 2 years of sales in terms of volume, the number one area that is seeing tremendous growth is the 3D printing or additive manufacturing that is shown in the last segment. The next is medical apparatus, dental application, and medical-based systems are gaining some traction. Optical fiber, electronic adhesives, and printing plates, um, metal decorations are also gaining some momentum. So these are some of the top growth areas that we are noticing. And if you look at the worldwide raw materials used for UV and EB curing, and what is the split, nearly 50%, nearly one half of all the formulations are monomer components. The monomers are one of the key components of the formulas. Oligomers is about 40%. The rest is divided between the photoinitiators and the pigments and additives. And what are some of the applications that we are seeing worldwide and also in Europe? The worldwide raw materials use is about 489,000 metric ton. In Europe, it is about 150,000 metric ton. So a significant share of that world market is Europe. And worldwide, you see industrial coatings accounting nearly 44%, which is the single largest application. Also, you see in lacquers and electronics, printing inks, and others. In Europe, one of the key areas is wood coatings, which accounts for nearly 38%. And then there is plastic coatings, PVC flooring, metal coatings, and also lacquers, printing inks, and electronics. So this is kind of a trend or the current state of market. What are the spread across different applications? Some of the trends that we are seeing in the UV lamp technology is the LED market LED based UV curing is on the rise, and for currently it's around 10 to 15% of the market share is LED lamps, but it's projected in 2023 it's expected to grow up to 35% of the market share in terms of the cost. $269 million in sales is projected for 2023. And as this is based on the cost, But as the LEDs get better and better and the cost keeps coming down, for the same amount of money, a lot more LED lamps will be used than the mercury vapor lamp or other medium pressure lamps. So those are some of the trends that we are seeing, and here are some additional markets for UV application based on the old SIC codes. Now it's called NAICS code in US, which stands for North American Industrial Classification System. But this just to show what are the end use applications that we see in the current market. So that brings us to the um, of, completion of our presentation, and perhaps in the, maybe I'll take just 2 minutes to go through some of the key highlights of a conference that I participated this year on this technology called RadTech 2014, and want to show you some of the new product lines and new areas that are coming up, and also included some vendor contacts, emails, and addresses that you can follow up in case if you want to get additional information. So RadTech is a non-profit trade organization, and that has more than 700 members. If you go to radtech.org, they provide a very detailed information on various market projections and key trends. And they have reports that addresses a lot of the growing areas, growth opportunities. That's the organizing agency that did the conference, and we had nearly more than 100 plus vendors showed up in this conference. Um, so what I've listed here is just the equipment vendors, the ultraviolet equipment vendors as well as the electron beam equipment vendors who came to the trade show, and these are some of the vendors that you can go to their website for additional information. Um, so these are some of the technologies we have done some testing in our partner lab and have some interesting information. And you can see that printing is an important thing. You can see a lot of printing, um, removing the packaging material and directly printing on the bottle or cans is becoming a more and more common trend. And what you see is here is um, propane tank, and this tank is cured is curing going through a curing process with the different these are the ultraviolet lights that are focused on different areas. One of the advantages is since there is um, no thermal energy, even a filled up propane tank can go through this and get it cured as it's going through the final end product where it is ready to be shipped. So that's shown here, and I'm just going to go through quickly to show what are the different product lines that we have seen. This is a microwave powered UV source that you are seeing here in this particular picture. And as I was pointing out to you earlier, these are the chips packet, the lace chips and the sun chips and various other um, things that we come across on a day-to-day basis. And this vendor said they can go up to 1500 feet per minute line speed to get this kind of rolling um, uh, printing taking place in the rolls. So that kind of high productive high line speed is possible with electron beam. This is the new LED based systems. You can see that there are nearly 480 LEDs in this small strip that is capable of turning on at different areas to provide curing to different parts. And there are other companies that has different light sources and other equipment manufacturers. Um, so this is Bayer. Bayer is another company that has big in chemical formulations, but they also have formulations for wood based curing. And you're also seeing this is the wine bottle type was talking earlier, where instead of a paper-based sticker, they have directly coated on their bottle. So these are some of a few other resources that if you want to get more information on this documents, there could be many more, but these are some that could help you gain some understanding of the UV and EB curing. So with that, I would like to see if you have any questions, and